Hello, everyone, and welcome to the live stream for today, Tuesday, November 29th. So we are almost at the end of the month, about to begin December. And here in the United States, we just finished Thanksgiving. And we also, for our team, we launched a new course, which we will talk about in a little bit when we've had a chance to let all the viewers join us. My name is Matthew. I'm one of the course staff, so we run this as part of our online classes through Coursera, but we welcome anyone who finds us from anywhere. So we're happy to have you join us. I'm going to hand this over to you, Chris, and you can welcome everyone, and we'll get started with questions.
Okay, it's good to have everyone here, however you found this, from one of the MOOCs or just stumbled upon it. And I'm happy to answer questions about astronomy starting right now.
And just so you all know, I'm aware that there is a little bit of a weird sound to my audio. I'm not sure what's going on. I'll try and fix it during the stream, but it shouldn't impact our questions. So the very first question for today is from Daniel Hoy, who's on with us live. How might we ever know or test whether at least some of the Albright meteorites might have Mercury as their origin?
That's an interesting question. It's actually hard when you have meteorites and you haven't actually watched the meteor land and therefore have a trajectory. It's very hard to understand the origination of certain meteorites. So we have meteorites from a variety of locations. We have Martian meteorites. There's well over 130 of those now that are cataloged on the NASA website. And we know from the geology that those are from Mars. There's a significant number of meteorites from the moon too. But for some that might be from a place like Mercury, another rocky planet, it's very hard to be sure because the mineralogy actually doesn't help too much since we have never had a lander or a rover or detailed geological experiments on Mercury. So we're sort of guessing what the chemical composition is. So when we don't have detailed geochemistry and we don't have obviously the trajectory of the object before it landed, then we certainly may never be sure. So it's pure inference to imagine that there could be meteorites from Mercury.
Excellent. The next question is from Demetris, who asks, why do black hole accretion disks mainly emit in the X-ray spectrum, whereas black hole jets have a significant radio wave emission component?
That's a good question, and astrophysics is interesting and it explains this distinction. So the material that swirls around the equatorial plane of a black hole, usually from a companion, if it's most black holes we know that are stellar mass black holes are in binary systems, that material as it swirls in is of course has an enormous amount of gravitational potential energy, and as it's pulled towards the innermost radii of the accretion disk, which extend maybe 10 or 20 Schwarzschild radii from the event horizon of the black hole. That material is accelerated and heated, and partly just by acceleration and partly by friction, viscous friction in the plasma, to temperatures of 100,000 or 200,000 degrees. And the higher temperatures go to the inner edge of the accretion disk compared to the outer edge. So the outer edge may be at 50 or 80,000 Kelvin, and the inner edge may be at a few 100,000. Those are the cooler temperatures of the outer accretion disk are hard UV and soft X-rays, and the inner accretion disk is medium to hard X-rays. And so it's the temperature of the plasma that dictates the emission. For the jets around a black hole, which tend to emerge from the polar axis, it's much lower density medium, and so we're talking about a very low density plasma that's being radiatively accelerated away from the black hole. And in that mode of acceleration in a very low density medium, much lower density than the accretion disk, then the radiation happens at a much lower wavelength, a much longer wavelength, and so that amounts to radio waves. So you can have an X-ray accretion disk while you have radio jets with a black hole.
Excellent. The next question is from Wendy Traver, who sent an email. If each portion of the spectrum from gamma rays to X-rays to radio waves have different frequencies and energies, why do they all traverse the universe at the same speed, as in the speed of light, or is my premise wrong?
No, it's correct. All forms of electromagnetic radiation travel at the same speed, 300,000 kilometers per second in a vacuum. The speed of light, but also the speed of radio waves all the way through X-rays. The physics of this was first established by James Clerk Maxwell in the second half of the 20th century. Maxwell, a fellow countryman from Scotland. Sidebar on this, if you ever go to Edinburgh, one of the second-tier tourist attractions, but maybe a top tier if you're a scientist, is James Clerk Maxwell's house. It's in the Georgian old town of Edinburgh, a very nice part of the town, and it's very well preserved with his experiments, his books, his diaries, his journals, and the furniture from his house. So that's a place I recommend. So the masterwork of James Clerk Maxwell was to unify all these various forms of radiation and recognize that they are all the same fundamental phenomena, which is coupled electric and magnetic oscillations, where the orientation of the electric and magnetic fields are 90 degrees apart from each other. And those coupled electromagnetic oscillations, in the theory, have one speed, regardless of wavelength, energy, or frequency, and that is the speed of light. So it was Maxwell's theory, the electromagnetic theory that's taught to every freshman physics student, that explains why all these forms of radiation have the same speed.
The next question is from Rami, who asks, if objects appear to take an infinite amount of time to fall into a black hole from our perspective, then how does a black hole grow? How come we can detect supermassive black holes or merging black holes if everything seems to slow down and sort of freeze at the event horizon?
That's an excellent question. It's sort of an illusion, basically. The relativity of the situation is that indeed, as seen from outside, something falling into a black hole has its radiation gravitationally redshifted. That's the physical phenomenon that's happening. It's a gravitational redshift. The radiation struggling against the gravitational field is redshifted or stretched to longer wavelengths or lower energies. And in principle, at the event horizon, that stretching or redshifting is infinite, and so it's reduced essentially to zero energy and becomes invisible. However, in the relativity of the situation, in the inertial frame or the reference frame of the object falling in, the object is on a ballistic trajectory and it simply falls through the event horizon to the interior of a black hole and serves to make the black hole a little more massive and a little larger. So what happens at the event horizon as seen from outside is essentially an optical illusion based on general relativity.
The next question is from Tom O'Brien. For redshifted planets, do we have an idea of why and where they are moving towards?
Well, planets, exoplanets, I presume we're talking about, not in the solar system. Exoplanets have their motions measured by the Doppler effect. Now, typically that is just a periodic sinusoidal motion that's used to determine the orbit based on the wobble around the star. For planets that do have an overall net motion, they may, of course, be moving through the galaxy, and some of them may indeed be liberated from the galaxy. We do think there are free-floating planets. We think that planets can be ejected from their solar systems, and if they're ejected in the direction away from us, of course, they'll have a significant redshift. However, there are also essentially equal number statistically of planets that will get ejected or sent in our direction and so have blue shifts. So it's not a universal phenomenon that exoplanets have redshifts.
The next question is from Pramod, who asks, how are all the viruses and bacteria removed from a rover so that they are not introduced to the surface of Mars when the rover lands there?
Well, that's a good question because it's obviously not done in a lab or a sterile environment. It's not done by technicians. It's not done by physical, interfering with the rover itself. Essentially, the rovers, when they're delivered to Mars, are not in a sealed situation. And so they're exposed to the outside world. And the outside world, of course, is the intense, almost total vacuum of space, a vacuum that's also filled with high-energy radiation, cosmic rays, and solar radiation. So because the rovers, as they're delivered to Mars, are exposed to this very harsh, sterilizing environment, the rovers are essentially sterilized. And so the space environment does the job. Once they land, of course, they're in a slightly different environment. Mars has a thin atmosphere. And so no decontamination takes place when they're on the surface. It all happens before they get there.
The next question is from Harry Bell. Do you have any thoughts on ventures like the Galileo project at Harvard? How likely is it to make a meaningful contribution to our understanding of the universe and to alien life versus being a pet project of the very rich?
I guess I can't answer this. I'm not sure what the Galileo project is at Harvard. I'll have to look it up. I'm not familiar with it.
Okay, how about something like Starshot or one of those other, you know?
So Starshot, Breakthrough Starshot is a project of the very rich. It's Yuri Milner, a Russian philanthropist, industrialist who is a billionaire essentially, who's given close to $100 million to Breakthrough Starshot, the attempt to send nanobots to Proxima Centauri, solving an enormous number of engineering challenges to be able to do that. So these projects are interesting because the private sector is starting to put money into space science and planetary science. There's another project funded by the same person called Breakthrough Enceladus, which is the idea of going to that moon of Saturn that appears to have icy jets and all the ingredients for life long before NASA will ever get there, which is at least 20 years away. Breakthrough Enceladus claims they can get to Enceladus for a tenth the cost of NASA and in about a quarter of the time. So these industrialist or these billionaire-fueled space projects are quite interesting. We don't know if they'll all succeed, but if any of them succeed, they're doing something that NASA basically doesn't have the budget to do.
The next question is from Dude, who's on with us live. Wouldn't the huge amount of radiation received make the possibility of life difficult on Europa? And why does Europa get more attention in this regard than Enceladus or Titan?
It's true that Europa is in an intense radiation environment. It's obviously in deep space. It has no atmosphere to speak of, and it's in the strong radiation belt of Jupiter itself, which has a very strong magnetic field and radiation belts, sort of analogous to the Van Allen belts on Earth. So there is intense radiation coming to the European surface, and so that's pretty much guarantees there's no life on the surface. All the interest in life in Europa is below the surface, below the ice pack in the subsurface oceans. Europa does get a fair amount of attention, but Titan and Enceladus do get attention. Titan is obviously going to be subject to a very ambitious mission from NASA, which will send on a lander the Dragonfly probes, essentially drone technology, to fly around Europa and sample the ethane-methane lakes for biochemistry. So that's a pretty ambitious mission for Titan. Enceladus also has a plan from NASA, but it's a 15 to 20 year time frame. So Europa just happened to get the highest priority. And that's because the Europa Clipper, which was originally a collaborative project with the European Space Agency, was funded by both agencies, and so it got to the head of the queue. Now since then the budgets have rearranged, the mission design has changed substantially. NASA is going to do part of the original concept alone, and the Europeans are sort of doing their own related thing.
Excellent. Well, why don't we take a moment to talk a little bit about the new course that we just launched. Chris, I will let you explain it, and then I will go grab the URL and post it in the chat.
Sure. Everyone who's seen any of my lectures or taken any of the existing MOOCs is welcome to check out our new MOOC for Coursera. It's called Knowing the Universe, the History and Philosophy of Astronomy. And it does include some modest amount of material from the astronomy MOOC itself and even the astrobiology MOOC, but it really is quite different in concept because it has the full sweep of the history of astronomy, from prehistory through the ancient Greeks to the Renaissance, to the period of time when we mapped out the Milky Way and then the universe itself. So there are 7 weekly modules that cover that territory. The other thing that's featured strongly in the course is philosophy, the idea of how we know what we know, the sort of principles of how science works, and how philosophy ties into our attempt to answer experimentally some of the most profound questions about the universe we live in. So there's a lot of high-level concepts involved, especially on the philosophical side. The history is interesting. There's a lot of episodes of discovery and so on, covering a big sweep of time. So I recommend that course, and I suggest you all check it out.
Great, and as I said, the link is in the chat. Daniel, who's on with us live, says he's already in week 3, so he's speeding right through it. Congratulations, and thanks for checking it out. And if you are here from that new course, welcome. We hope to see you a lot more. We do these live sessions every 2 weeks approximately, and there are a variety of ways to find out. We always email, and then there's information on the forums in the course. All right. Oh, I've been informed that our timing is terrible because apparently Patrick McEwen says, I don't mean to complain, but I do want to point out that the session begins right in the middle of the U.S. Men's World Cup game that will determine whether or not they advance to the knockout round. Right.
And as someone who holds 2 passports, I'll notice that we're also conflicting with the England-Wales game. So two British countries are battling it out at the same time.
All right, Stanley, who's on with us live, asks, can you talk about the superstar clusters which Hubble has imaged in M82? How did they form? And are they a mix of sizes or all massive stars, as some data suggests?
These are massive star clusters. M82 is a very massive galaxy, and it's one of the Messier objects, obviously. And so these superstar clusters they're not unprecedented. We've seen similar type star clusters in other disturbed galaxies. M82 is a peculiar galaxy, essentially. It's not a classical symmetric galaxy by any means. It's easiest to detect the most massive stars because the most massive stars are the most luminous. So I don't think the data is good enough yet to talk about the mass function or the mass distribution of stars in these clusters. But certainly these clusters have more massive luminous stars than we see in anything like our galaxy or any galaxy similar to the Milky Way.
The next question is from David Gold. Bruno was burned at the stake for ideas such as the universe is infinite and other habitable planets could exist. Do astronomers today face any taboos when publishing their ideas or discoveries?
No, nothing like the problems that people like Giordano Bruno had. Although I will point out that the Bruno story has been a little bit mythologized in the telling, in the history of it. He was burned at the stake for, quote, being a impenitent and pertinacious heretic, end quote. And actually, although he did hold quite radical views on astronomy, he believed that he believed in the Copernican system. He believed that there was life on other planets and that life might be more advanced than the Earth. So very advanced astrobiology ideas for someone over 400 years ago. But actually that wasn't what truly got him in trouble with the church. What got him in trouble with the church was he held theological views that were very much at odds with Catholicism at the time. And so the heresy that got him executed was really not an astronomical heresy. I think that's a sort of miscasting of history, because it's turned him into a martyr or a hero to science. And he was indeed a visionary, and he did indeed have some very advanced ideas, but that's not actually why he was executed. But since it's a package, he's one person who had all these beliefs, it's reasonable to wonder whether they didn't play a role in him being unpopular with the church, because these were unpopular scientific views. And so I'd imagine it is part of the story. Enormous chilling effect, of course. This was in the year 1600. Remember that within a decade, Galileo would start using the telescope for astronomy and lead to his own collision with the Catholic Church a few decades later. So he might have looked at the story of Giordano Bruno as a young man, and Galileo might have got an idea of what he was headed for.
The 800 millimeter telescope project asks, hello, Professor. Can you explain the stellar mechanism that makes Cepheid stars reliable candles, and why are they so consistent?
So there are many kinds of variable stars in the universe. I don't remember the exact number, but it's over 40 different types of variable stars. Some of these variable stars are irregular variables. They don't have any particular period. They're episodic, flaring episodically. A nova would be an example of that. Nova are recurrent phenomena, but they don't occur on a particular time scale. They're quite spectacular stellar cataclysms, in fact. Then there are a more particular class of stars, and there are a number of them, which are called pulsating variables. And these are stars where there's essentially a thermostatic mechanism in play, where the star is on the edge of an instability due to the way the nuclear fuel is being consumed, and it leads to an instability that gradually puffs out the star, which lowers the temperature, which reduces the fusion rate, which allows the star to contract again, which increases the temperature and increases the fusion rate. And so this can set up an oscillation, and it can set up a pulsation, and that means there's a period. So Cepheid variables and Lyrae variables and another handful of variables have that particular property, that their pulsations have a particular frequency. And the use of Cepheid variables is the fact that the period of pulsation is very tightly correlated with their luminosity, which is also a consequence of the nature of this mechanism, this thermostat mechanism I mentioned. And because of that tight coupling between period and luminosity, you can use Cepheids as distance indicators, because if you know what their period is, you can predict what their luminosity is, and then how bright they appear plus their distance gives you the luminosity. So they become distance indicators. A very powerful tool in astronomy.
The next question is from Bernard, who asks, it seems like focusing on manned exploration of Mars while also devoting the same resources to unmanned exploration could probably make science or the understanding of Mars and the universe progress faster. So why don't we do this? Why don't we do manned and robotic exploration? Is it just because of politics and nations' egos?
I think in the end we will do both, but the big distinction here, and it is a big distinction, is that pound for pound or mission for mission, robotic missions are dozens, if not hundreds of times cheaper than manned missions. To get even a handful of humans to Mars, and you probably have to have a crew of 3 or 4, they have to be able to survive in space for 8 months, 6 to 8 months each way, and because they will not be able to, they have to have sufficient food for the round-trip journey and a stay on Mars. So you're talking about roughly 2 years of critical supplies of oxygen, water, and food. So the payload and the mass of the spacecraft is substantial, and that means the energy cost is enormous. By contrast, these small rovers we send benefit from the miniaturization of electronics, and so you can get an enormous amount of scientific power in a package, and essentially they're invulnerable. We know the Opportunity and Spirit rovers lasted far longer than the 3 months they were designed for. So we've had rovers that survive on the Martian surface and do good science for a decade, and it's going to be a long time before there's a Mars base which will allow humans to do work on Mars for a decade. So I think it'll happen to send people to Mars, but the difficulty and expense of it versus rovers it's an enormous difference.
The next question is from Pramod, who asks, why is an object falling into a black hole and losing information an issue when it seems like the same thing happens when an object is burned?
Well, something similar does happen when an object is burned, but you could argue that the information is not completely lost when something is burned. So when something is burned just by combustion, for example, that's a chemical reaction, and as we all know, we've seen this in movies and books, and sometimes it happens with books. When you burn a book, the ash does actually still contain information. Unless you completely grind it to a dust, you've not destroyed the information. So burning does not as readily destroy information as falling into a black hole does, which completely destroys all the information of what went into the black hole.
The next question is from Ellensburg, Washington, who's on with us live. Good day, Professor. It is said that Jupiter's closest moons actually shrink as they spin around Jupiter. Because of Jupiter, is this shrinking visible, and how come the moons do not disintegrate?
I'm not quite sure what the effect you're talking about refers to, but what is true is that the closest moons of Jupiter tend to be small moons, and they're subject to extremely strong tidal force. Because they're in slightly elliptical orbits, because they're fairly close to the giant planet, the most massive of all the planets, the stretching force on these moons is substantial. So rather than sort of shrinking wholesale, these little moons are being distorted, stretched, pulled, and tugged, and it's possible that they reconfigure themselves because of this tugging and stretching to a more compact configuration. But that's a very subtle effect, and I don't think we've actually measured it.
Excellent. And yeah, I do believe that's what they were talking about, shrinking in terms of like one direction or the other temporarily, so that tidal forces. The next question is from Abdullah, who asks, would life not be present on Earth if a single massive planet like Jupiter, which controls where a majority of the asteroids remain, wasn't present?
It's an interesting hypothesis. So it's been speculated that Jupiter's role in the solar system and the fact that the Earth is a living planet is not entirely a coincidence, that Jupiter is essentially a guardian of the Earth in the inner solar system. And it is certainly true that some fraction of the incoming objects, Earth-crossing trajectories, are deflected out by Jupiter. But of course, Jupiter is only at one point in its orbit and takes 12 years to go around the Sun. So it's a rather inefficient guardian in the sense that it doesn't really protect us fully from objects coming in. It also doesn't protect us from objects that come in from orthogonal to the ecliptic plane. In other words, things in the Oort cloud that are perturbed, the comet cloud that are perturbed and come in essentially vertically, and Jupiter is not in an orientation to affect that. So yes, Jupiter has and does protect the Earth from some fraction of incoming objects, but really not the majority of them.
And then a quick follow-up to Bernard's question about robotic versus human missions. I guess the question that he was interested in is, why don't we spend all of our money on robotic missions? Why do we have manned missions? Do we do human missions because nations want to like have egos and want to show off their capabilities, or are there legitimate reasons for having human missions?
Yes, so that's also a good question, and I think the simple answer is I agree with the premise of the question that it would just be far more efficient, more effective scientifically, and far more cost-effective to use entirely robotic missions, especially to the planets, to Mars and other planets, and even the Moon. It is so much easier, so much cheaper, so much more bang for the buck. So why do we send people? Yes, it's about geopolitics, it's about national pride, it's about that human urge for exploration. Remember, the taxpayer in the United States and other Western countries pays for all this, these space programs, NASA itself, and the taxpayer has to feel excited or involved in what's happening. And while the taxpayer in the US they've grown attached to those nice little rovers, of course, and anthropomorphized them a little bit, there's no substitute for having people there, because then you can empathize with the bravery of the astronauts in a harsh environment and be part of a human story of exploration. So I think it's the reality of that emotional connection to the general public from human exploration that keeps NASA very much invested in human exploration, even while everyone within NASA would admit that it's far more cost-effective to use robots.
Excellent, thank you. Damir, who's on with us live, would like to know, what is consciousness from the cosmic perspective?
Well, consciousness is one of those elusive concepts that science has simply not been able to understand and perhaps even define. I don't think astronomy or cosmology gives us any extra insights into consciousness. Somehow, and it's maybe a miraculous thing, it's remarkable at some level, the universe, which is full of inert objects, which is full of atoms and molecules that collapse into planets and stars and galaxies, somehow in this scheme of purely physical objects described by physical forces and chemical reactions, consciousness has emerged on this planet in species like humans and in a handful of other species. We don't know how that happened exactly. We don't really know why it happened as opposed to not happening at all. And we certainly don't know if it happened on any other location in the universe. So consciousness is really one of the most profound mysteries of science, because brain scientists haven't figured it out. And as far as the universe itself, we're hoping, obviously, to be able to find examples of consciousness somewhere else. And that would give a whole new field of science its birth, basically.
The next question is from Faisal, who asks, why is there water on the south pole of the moon, and we don't hear about the presence of water at the North Pole?
That's a good question. It's not a completely asymmetric situation. There is some water. There's subterranean water all over the moon. In fact, the mid-latitudes have a little bit of it. And most of the water is in hydrated form, attached to minerals, and little subsurface ice deposits. Part of the reason there seems to be more ice on the moon is that there's an enormous feature on the moon's south pole called the Shackleton Crater. Shackleton Crater is one of the biggest craters on the moon. And in the rim of that crater, you have heavily shadowed regions just because of the orientation and the depth of that crater. And those shadowed regions in that crater provide an enormous place where you can put ice and where ice will not sublimate or evaporate. So it's partly because of Shackleton Crater that the moon's south pole has a lot of ice. But there is some ice on the north rim of the moon and the north pole of the moon as well.
The next question is from Pramod, who asks, did the orbit of Earth change over time as it accumulated meteorites? And are there any theories on what percentage of Earth's mass is made of meteorites?
That's an interesting question, because yes, in principle, if the Earth accumulated mass early in its history, or at any point in its history, then that would affect its orbit. Essentially, that would give it more energy of motion, because the energy of motion is half the mass times the velocity squared, and you've increased the mass a little bit, and that would alter the energy balance in the orbit, and so move it to a slightly larger orbit. This is not really a measurable effect, though, because the truth is that the sum of all the meteorites that hits the Earth is really not very much at all. I can't remember the exact number, but I think it's of order 100 tons a year of stardust or meteor material falls to the Earth's surface. 100 tons compared to the billions of trillions of tons of the entire Earth's mass is tiny. It's just negligible. I think the only time that the Earth gained any significant amount of mass was soon after the formation, when there was still a lot of debris in the solar system, and where the heavy bombardment era happened, which included some very large impactors, things that were 100 or 1,000 kilometers across, and also a lot of comets. That may have added significantly to the Earth's mass and changed its orbit measurably.
So this next question from Jaleel came from an email, and I'm not sure exactly what it's asking, so I think we can try it in two different ways. So the question is, how can someone recognize telescope material in space by infrared? So the first way I can interpret this is, how do we recognize infrared images that come from space telescopes? How is it possible to tell that an image is taken in the infrared?
It isn't always possible, because infrared images, of course, represent invisible radiation, so the eye can't see it. So anytime you see an infrared image on the web or in a printed publication or on a NASA website, that is false color. So that's someone who's taken the intensity of radiation at an infrared wavelength measured by an electronic detector and just converted it into a color or a grayscale. So you're not really looking at a real map. And so that doesn't actually tell you. I think the only clue, or the only way you could infer that an image was infrared as opposed to optical, was what the image was of and what it looked like. An infrared image is essentially a heat map. So if the object you're looking at has volcanoes, say, and the volcanoes all glow brightly in the radiation of the image, then it's a good bet it's infrared radiation. So that's an example. Anything where there's hot and cool, and the infrared will track the hot. Another way, in a different context, that you could tell an infrared image is if you're looking out in space through a region with a lot of gas and dust. Visible light is extinguished or quenched by gas and dust. So if you see through a region of space where there's a lot of gas and dust, and you see through it in the image, it's probably an infrared image. Best example of that is the center of our galaxy, which is opaque to visible light. No, essentially 1 in a trillion photons, invisible light, gets to us from the galactic center. But we've made images of the galactic center with infrared radiation. So if you see such an image of the center of ours or any other galaxy, it's more likely to be infrared than visible.
All right, so the other way to interpret this, I think, is how do astronomers who are looking at infrared images recognize material in space? So how do they know what it is that they're looking at when telescopes point at objects and look at them in infrared?
So just by making an image, you aren't always sure what something is. Just the morphology or the shape or the texture even doesn't always tell you what you're looking at. Obviously, if it's a planetary surface or a moon surface where you're seeing through the atmosphere to a surface, you can infer that you're looking at a surface. You'll see geological features, and the geology will show up whether it's infrared or visible light. But in other situations, you simply may not be sure what you're looking at. So infrared reflecting the hot zones more than the cold zones, you may be just looking at a very warm object compared to the coldness of space or the coldness of other parts of the universe. So it's not a completely reliable process. To get more information than just the color, the infrared color even, of an object, you actually need spectroscopy. So you've got to take that infrared light and spread it into a spectrum and look for features that will tell you what chemical elements that material is made of.
Excellent. The next question is from the user Ellensburg, Washington, who's on with us live. Are all stars, like our sun, destroying anything that gets near it? Or are there other types of stars which humans can actually go near to produce energy without getting hurt?
Well, the sun is a middle-weight, middle-rank star, which obviously emits a lot of radiation. And so it is indeed dangerous to get close to the sun. There are possible ideas out there to harness solar radiation by sending concentrators or collectors close to the sun, quite close to the sun, maybe closer than the orbit of Mercury, and then beaming it back to the Earth. Those are very advanced ideas, almost science fictional. If you wanted to get very close to a star, you'd have to pick a red dwarf. So red dwarfs are 10 times less massive than the sun. They are thousands of times less luminous than the sun. So in principle, you could approach much closer, dozens or hundreds of times closer to a red dwarf than you could to the sun. That's about the closest we could get to a star. And if you go to the bottom end of the stellar spectrum, or mass scale, to the things that are barely stars at all, those surface temperatures are actually quite modest. Their surface temperature is only about 1500 Kelvin. That's still extremely hot, but certainly spacecraft could withstand that.
The next question is from Dude. What would be some of the major differences if life originated in non-polar solvents on Titan compared to the polar water-based life on Earth?
Well, if life actually could exist or does exist on Titan, its biochemical basis will be completely different. So as the question implies, life on Earth is based on the solvent water. Water is a polar molecule, which relates to its electrical conductivity and its activity, and it's sort of how the electrical charge is distributed in the water molecules. It's a very good solvent. It also, by the flip side of being a good solvent, is that it's quite corrosive. So it actually dissolves minerals and chemicals. And so if you're trying to build complexity, which you need to go from chemistry to biology, it's not clear water is always a wonderful thing, but obviously it led to life on Earth. Now, if your solvents or your liquid medium is different, and on Titan it would be ethane, methane mixed with a little water and some ammonia and some acetylene and other more extreme compounds, it's not clear how that would work. It's possible that you could concentrate simple chemicals and form complex chains and perhaps replicating molecules. But no one's been able to do a lab experiment under Titan conditions. It's extreme conditions, of course. It's very low temperature and low pressure and exotic chemistry. So simply we don't know what might be happening on Titan. We'll have to go and find out.
Excellent. The next question is from Amara, who's on with us live. I would like to know if something falls into space, which direction does it fall into? Like, does it go up or down? Does it stay stationary?
Well, it's of course interesting because on Earth we just take our reference frame completely from local gravity. So, for us, down is the direction the gravity's operating and up is the direction opposite it. Of course, that's our local gravity on the opposite side of the Earth in Australia or New Zealand from the US. They're declaring the opposite direction to be up and down. So right away, it's a relative concept. If you just have a general object in space falling, it depends where it's falling to and away from. An object could be falling towards one planet but away from another. So which do you choose as the reference frame? It's a little arbitrary. So out in space, you have an arbitrary reference frame, and when you're outside the solar system, the sensible reference frame is the galaxy itself. So we could reference motions to the orientation of the galaxy, the plane of the Milky Way disk, or the perpendicular plane that goes into the halo.
Excellent. The next question is also from a live participant. See here, Natalie would like to know, do you know of, or can you talk about programs that you might recommend for a graduate program in astrobiology?
Astrobiology is a very exciting and a booming field driven by exoplanet research, but also other fields trying to look at how life formed on Earth and synthetic biology, the possibilities of biology elsewhere. So it's a growing subject, but at the graduate level, there's still not a lot of offerings. I think there are only 3 astrobiology graduate degrees out there, PhDs, and I won't be able to name all of them. The program I'm most familiar with is the graduate certificate at the University of Washington, which has existed. It's the longest lived of these astrobiology graduate programs. So it's not a full PhD, it's a certificate that you attach to an astronomy PhD by taking a set of courses in astrobiology. But it's a very good program. It's been going for decades, and I was involved in evaluating it 10 years or so ago, and it's had very good success with its students. So University of Washington is probably the one I'd recommend the most, just because it has a really good track record.
The next question is sort of related to that earlier question about directions in space. Rentgen 101 asks, if you are in the center of our galaxy, how would you set your 3 dimensions X, Y, and Z in space?
I think if you're in the center of our galaxy, it would be quite difficult, but you could still use galactic coordinates, or galactocentric coordinates. If you were right at the center of our galaxy, of course, you would feel no net gravitational pull from the Milky Way because it surrounds you as if you were at the center of the Earth. But you would be able to determine, if you could see out far enough, the plane of the Milky Way, which is where the rotation is in the spiral arms. So you definitely have a reference frame, and it's a sort of altitude azimuth reference frame, where the altitude would be the elevation above the plane of the Milky Way disk, and the azimuth would be the orientation in 360 degrees going around the disk.
The next question is from a live participant. Which domain of life makes the better model organisms for possible life on another planet? Archaea or bacteria? And what features make it a good model organism?
Well, of the branches of the tree of life, the one most recently discovered in the 50s and 60s, I think, by Carl Woese, who's one of the main architects of this astrobiological concept, is the Archaean branch of life. So Archaea are bacteria, but there are bacteria whose DNA sequencing suggests they formed first, earliest to the root of the tree of life, and also suggests that they formed in hot, medium hot to hot environments. And that could have, of course, have been near undersea deep thermal vents, hydrothermal vents in the oceans. So Archaea are probably the best model organism because that possibly and probably was the first domain of life on the Earth itself, and in a hot primordial planet, we imagine that's what would start first.
Amara would like to know, if the Earth's magnetic field reverses, does that mean that the Earth will rotate westward, so the sun will rise in the west instead of the east?
No, it doesn't actually change the overall rotation of the Earth. So the the flipping of the Earth's magnetic field every few tens of thousands of years is associated with the fact that we have an entrained magnetic field, but we also have a liquid metal. There's a solid core, but there's also a liquid core, and the field can move, it can reconnect, and it can reform because of that liquid core and the way that it spins and creates a dynamo effect. But this is all just relating to the magnetic field, and of course once it leaves the Earth's surface through space, it interacts with electrical fields too and creates radiation. But these are electromagnetic effects, and they do not affect the overall angular momentum of the planet. So the angular momentum of the planet, the direction in which it spins, is not affected at all by these electric and magnetic phenomena.
The next question is from an email regarding the event horizon of a black hole. I understand that from our frame, this is similar to an earlier question of reference, things falling into the black hole would appear never to pass. But in a pair of black holes or even neutron stars getting eaten, how is the time frame, or how are the events of this event affected?
Well, if black holes, say, are merging, or an object, a star, or some other big object is falling into a black hole, it does indeed have a trajectory and a movement defined by gravity, and that gravity means that it will fall in, add to the mass of the black hole, create some gravitational radiation, and so on. So we think that that is what happens. So things fall in according to their kinematics and their trajectory and their initial angle of approach, and they do indeed add to the mass of the black hole.
The next question is from Drishti, who asks, how do you think that quantum mechanics, or how are quantum mechanics and astrophysics related?
Well, quantum mechanics is at the heart of astrophysics, because astrophysics is sort of about how particles and radiation interact and are structured and organized in the universe. And in the end, if we're talking about fundamental particles, and the universe is mostly made of simple things like a plasma, where the protons, of course, the fundamental element of the universe is hydrogen, which is just protons and electrons. The hydrogen atom is described by quantum mechanics. The electron and its localization is described by quantum theory, and so is the proton. So all the simple ingredients of the universe are described by quantum theory, either in the lab or out there in the universe where they occur. So applying quantum theory to astrophysics happens all the time, essentially, in all domains. Sometimes it's complicated astrophysics, such as when you have an accreting object or a black hole with a magnetic field, and you're looking at the interactions with the magnetic field, but it's still quantum theory that is underneath it all.
The next question is less of a question and more a comment that one of our participants has said that they would really love to have gone to space on the last, on this lunar mission that is orbiting the moon now. Can you talk a little bit about that mission and what are some of the scientific goals or even geopolitical goals of going back to the moon?
So Artemis 1, which is the most recent moon mission from NASA, which is the Space Launch System, the SLS is the launch system, and Artemis is the name of the mission. And it sent a capsule to the moon, and it circumnavigated the moon, got within, I think, 60 kilometers of the moon's surface at one point, and then head back to the Earth, about a week each journey. It's a proof of concept. It didn't carry people. It actually carried, I think, 3 crash test dummies. They're sort of fake bodies triggered out with sensors to try and measure the effect of vacuum and zero gravity and radiation environment on a sort of humanoid robot, if you like. They're not actual robots, they're just dummies, if you like. Artemis 2, the next mission, probably at least a year away, will have a crew. It will be a crewed mission, but it will follow a similar trajectory and it will not land. And these are just to prove the systems, to prove the life support systems, the safety systems, because the landing itself is the most hazardous thing, so you don't do that first. And this is similar to Apollo 8, which was the precursor, of course, to Apollo 11, where the first landing occurred. So you first tested it out by sending the Apollo 8 astronauts around the moon when they didn't get to land on it or set foot on it, but you just showed that the Apollo systems worked. Artemis 3 will be the mission that lands on the moon, where NASA has already committed to putting a woman and a person of color into that crew for Artemis 3. And these are geopolitical goals, of course, because the Chinese are very actively involved in space. They currently have sent a spacecraft up to occupy their newly completed space station, so they have a fully fledged space station of their own, not collaboratively with 20 countries like the International Space Station. They also have plans to go to the moon and to go to Mars. So there's absolutely some geopolitical juice behind the Artemis mission. And it's not cheap. The estimated cost for Artemis 1, 2, and 3 is over $90 billion.
The next question is from Anas Anwar, who asks, what if our universe itself is a black hole?
Well, it is conceivable that the universe itself functions like a black hole. It's not formally like a black hole, because to be a black hole it would have to have a high enough mass density to meet the definition of a black hole, and it would have to have an event horizon. There's no indication that our universe has an event horizon. It does, however, have a horizon, but it's more of a cosmological horizon than an event horizon. The distinction being that our universe has a horizon, or a limit to what we can see, based on the time it takes light to reach us in the history since the Big Bang, or the fact that the expansion was very fast early on, and so there are regions of space that have been moving away from us so fast that no light could reach us. And that, you can see, is conceptually quite different from an event horizon of a black hole, which is a static surface which prevents us seeing inside.
Dude would like to know, is oxygen necessary for complex life? Can anaerobic organisms be as complex as aerobic organisms on another planet or moon?
It's a good question. We don't totally know, because the biology experiment of the Earth played out in one particular way, and we can't really see how alternatives would occur. But it's certainly true that the metabolic complexity of anaerobic organisms is fully the equal of aerobic organisms. You can just look at and we're talking about single-celled cells with nuclei. You can just look at the genetic material, the functional complexity, the metabolic pathways, and just how complex that is. So there is really no difference. Oxygen is not essential, really. We had a microbial ecosystem that was based on metabolizing methane for hundreds of millions of years before oxygen came into the picture. And there are other possible compounds or gases or even liquids that could be metabolized. So there's nothing special about oxygen. Oxygen, of course, becomes a special thing when photosynthesis is developed or invented by biological life forms, and that allows sunlight essentially to convert, to be captured from carbon dioxide and carbon taken out of the air from the carbon dioxide using sunlight as the energy source, and you can build biological material that way. So that's an incredible innovation, photosynthesis. But it's not the only way life can function.
The next question is from Bernard, who asks, with the expansion of the universe, could galaxies be forming beyond those we can observe today?
Definitely. The expanding universe includes regions of space that we have not yet seen, because in 14 billion years of the age of the universe, there's not been time for light to reach us. It also includes regions we may never see, because they are moving away from us faster than light speed, and their light will never reach us. And in those regions, either the ones we haven't seen yet because they're too far away, or the ones we will never see because they're moving away too fast, yes, it's entirely possible that galaxies could be forming, and we won't see it. However, more generally, in an expanding universe, the rate of galaxy formation does decline, for the obvious reason that the density of the universe declines. And so there's less material available to form new galaxies. What material there is more diffuse, more thinly spread out. And so the rate of new galaxies forming is now hundreds of times lower than it was at the peak of galaxy formation.
This is going to be the last question for today. It's 1:58. So once you're finished with this question, we can wrap up, and then we will send out announcements for future live sessions in the next week or two. Mammerker would like to know, and I'm not sure about the premise of the question, so you'll have to address that as well. Since we are now certain on the shape of the universe, do you subscribe to the multiverse theory and or an infinite number of universes?
So we are sure of the shape of the universe in the sense that space-time appears to be flat. So we live in what is a geometrically flat universe in 3 dimensions. And that has implications for the energy and matter content of the universe. The flat universe itself does not have any implication for the multiverse idea. The multiverse idea, with the exception that the current explanation for the flatness of the universe is that it went through a period of inflation in the first tiny fraction of a second. So if inflation is the mechanism by which space-time is flat, then it is true that certain variations on the inflation paradigm, the inflationary idea, can lead to other space-times being created or existing at the time that our space-time inflated to become the universe we see. So there's a consistency there with the multiverse idea, but it's not evidence for the multiverse. There is currently no evidence that the multiverse idea applies to the universe we live in, as interesting as it sounds. Thanks very much. A lot of good questions, covered a lot of ground, and I was glad to have everyone here, tell them about our new course. So thanks to Matthew for facilitating, and we'll definitely get in, I would say, 2 more live sessions before the end of the year.
Excellent, and thank you all so much for joining us today. As you saw, there are links in the chat up at the top, so you can check out our calendar. If you join our Google Calendar, we always announce our live sessions there. We also have a Twitch channel, and so feel free to check that out. We do some of our live sessions on Twitch, and we also have a whole bunch of other streaming activities going on our Twitch channel, and that's Teach Astronomy on Twitch. Take care, everyone, and I hope you have a great rest of your week and weekend.
Yes, goodbye, everyone.